Hello, everyone. My name is Piotr Modrzyk, and today I'm going to present you with our new achievement in the company, which we decided to share with everybody, with the community, and which is related to the problem of selective right grouping, which directly is affecting every storage system which is going to consider energy efficiency and different levels of energy states in the storage systems. So hopefully you will enjoy it, and let's move forward. So this presentation was presented together with the David Gerstein of in the Software Developer Conference in Santa Clara in year 2024. David is not today with me. However, he was the contributor to the slides, and he's also mentioned on this slide. And I am here on this side. I'm going to host you for the rest of this presentation. So this what we'll be talking today is going to be about energy efficiency, and in the aspect of energy efficiency in the context of the data storage. And I will try to guide us through some existing solutions, and then present our proposal for the problem, for the solution for the problem. And on the end, we will even show you the implementation details which we had during the process. And we have also some results to talk about. So we have already it on the live system. I hope you will enjoy it. So stay to the end, please. So the problem of the extensive distribution of data across the servers is producing a lot of challenges, and especially challenges in the context of the energy consumption. And especially if we have a lot of servers and a lot of drives which is running at the same time, the need of having some solution for managing these energy factors is growing. And basically, we would like to propose something which everybody could consider in their own implementation in the storage systems, and which could be also used in the large scale for the final products. And if you look at the pyramid of the data distribution, usually you see something like this, what is on the right side of this slide, when very little quantity of data is actually considered hot, and the biggest quantity of data is becoming cold or is cold already. And actually, according to the data which we managed to gather from our partners and also from the market, this proportion of having cold archive is around 60%. This is making the very direct need in the market for proposing something which will allow people to store this huge quantity of data in the energy fashion, in the energy way, and at the same time to have data actionable. And by actionable, I mean that, let's say, if you look at the, for instance, media industry, there is a lot of post-productions materials which is happening, which are being edited, but only a fraction of them is actually needed at the very moment. However, when they are really needed, there is to be taken from the archive system, there is usually a very unexpected delay to get them out. So the solutions which could offer immediate access to the data, and by immediate, I mean, let's say in the matters of minutes, not hours, right? Are having a very significant role for instance, such use cases. Also, we would like I would like to point out that this code archive, this code data, because they are growing, very often they are being considered as something which maybe people should get rid of, remove. And we would like to propose some solution which will make people to not to consider removing the data, because they can have something which is affordable and at the same time actionable. So it's fast accessible and taking possibly zero energy when it's not being used. And all of this is coming in the package with using the hard drives. So surprise, it's not about tapes. It is about medium, which is hard drives, which has ability to go into very levels of the power savings modes, including completely switching off the hard drives. And at the same time, have them very fast available to deliver the materials which are needed for, let's call it users, stakeholders, people who needs the data. So if you look at this energy inefficiencies, there was a lot of reasons why we could not do it in the past using the hard drives. Because, for instance, if you use the write systems, the write system, by the fact that they are using erasure coding, does not allow you to stop even one hard drive in the write system. And if you look at the problem from the point of view that these hard drives are running all the time, it means that many people were resigning from the archive system based on the hard drives, because when they wanted to have redundancy and safety of the data, which write systems are providing, at the same time, they could not switch off the hard drives. So this is why for a very long time, there was a problem how to do it correctly. There were approaches in the past, the big companies were trying to do it, and they could not do it. But there's a change which happened over the last years, and this change is called software-defined storage, which allow us to actually deliver right level safety, or even beyond right level safety, and at the same time allow to have control over energy consumption on the controlled energy consumption on the storage. So there are some existing solutions which are trying to tackle the problem, to try to make it, less painful, let's call it. And in the literature and also kind of semi-practical applications, I'm saying semi-practical because on the end, many of these solutions is not working. You have something like dynamic power management. So something which allow you to decide in what state the devices should go. You have a workload skew, which is another technique, and then you have a combination when you connect these two techniques together. So you have awareness of the data, of the workflows, and you have dynamic management techniques. And MATE, which stands for massive array of idle disks, was one of the implementations, which was, or let's maybe not call it implementation. It was the people were trying to achieve it by implementing the MATE, this combination of the DPM and WS together. However, this didn't work, and in the literature we can find a lot of examples provided by universities and companies which tried to use the MATE that it didn't work. And there's also another approach which is called popular data concentration, which is like another variant of mixing DPM together with WS. And also there's, of course, write systems, which we already said before that they are not very good because you can just not stop a hard drive when you use this write system. And there's another things like data deduplication. For instance, people were trying to say, okay, it's a lot of hard drives, but if we deduplicate the data, we have a less drives, so less energy, right? And somebody said, oh, what about compression? If we compress, then obviously it's less data, and it means less drives, so less energy. But none of this solution is, let's say, it's serious about stopping the hard drives and make them completely not to work. They just try to minimize a little bit the problem of the fact that the data are growing and they are cold, they are there, and they are sometimes needed, right? And even despite of being cold. And to be honest, compression is kind of, I would say, I don't want to say that this is a joke, but I already said it, so it's too late. Okay, so compression doesn't make any sense with the really big data. I mean, the real big data, what is it? It is a videos, right? We are talking about videos. This data is already compressed. So nobody is keeping raw data in the 4K or 8K resolution. There is always some compression involved, very high quality, and these data are basically not compressible. And the same is about image processing, which is basically a variant of video processing, right? Or the other way around. When the data is already compressed, the heavy data, the big data, which we are talking about, they're already compressed. So claiming that, for instance, LTO is saying, look, you can have a 10 terabyte LTO tape, and with compression, it is even 25 terabytes, is basically a lie, okay? It's a lie. It is not true. The data on the tape, which is saying 10 terabytes uncompressed, that's exactly what you are going to have. And there is a little probability that your data, big data in the terabytes or petabytes, is going to be compressible. I spent too much time, by the way, talking about this compression, but I just could not stop myself. So let's go to another slide. Okay, so of course, there's hard drives dynamic power management, and this is something which many of us is aware that hard drive have states like active, idle, standby, and even off. The problem is with the off. The off actually is very difficult to be achievable, because even if you can switch off the hard drive, usually you cannot switch it on because it is not supported by the main board or some other electronic. So every computer has the ability to switch off the drive, but not every computer has the ability to bring it back using the software. And the solution which we are talking about is assuming that in your storage, in your servers, in your JBots, when you will be using the hard drives which you would like to switch off, they will also support something which is called pin number 3 inside of the hard drive, which is basically power management switching on the hard drive ability. So let's move on here. I already talked a little bit about this, that we have this state, so I don't want to spend too much time. And I just wanted you to remember from this presentation that the pin number 3, which is about power disable functionality and also enable, is a very important functionality to actually achieve the full energy saving state when you will be building your storage systems. Okay, so there are unfortunately challenges related with the fact when we would like to mix together this DPM together with the workload SKUs. And one of them is, for instance, that it's very difficult to adjust dynamically this power states. It's really not easy to do it. Very often storage systems are having just one big, let's call it write system, which, or maybe it doesn't need to be a write system, it could be even the group of the drives. And this entire group is provided as a storage solution for some department maybe, and then it's very difficult to put in the sleep state this data, because they are basically still being used by somebody in the team. And to fully leverage this DPM, we should have some optimization on the data distribution. We should think about some algorithm which can provide us how the data should be stored, and at the same make sure that this is transparent for the user. So it's like it's our job as a storage service providers to give the solution which will do this kind of optimization of the data distribution across the storage systems. So let's talk about the solution which we have for this problem. And the name of the solution which we have is called selective write grouping. Let me tell a little bit more what we mean by the selective write grouping. So I will use the example of our typical deployment, which is 8 servers, and each of these servers has their own JBot, which is populated with from 60 to 102 drives. In our examples, we'll use the smaller version because it's also interesting by having this tail. And what I wanted to say that this solution can have a mix of any type of the medium. I mean, from the point of view of the drives, any type of medium, which is like host managed SMR drives or CMR drives, or SSDs or NVMEs. Okay, they can be mixed and they can be distributed across the servers. And it's very important that the servers which are implementing our idea have also support for the pin 3, which is a power disable feature. And this should be supported by JBots and also by the hardware, as I already mentioned before. And what is important is that this system is implementing erasure coding, which is giving state-of-the-art protection across the cluster on the level that any random two servers, like server 3, for instance, and let's say server 2, they can disappear together for some reasons. I don't know, somebody disconnected Ethernet cable, or maybe we have maintenance, we need to move a server from one rack to another. So they can be switched off, and even up to 2 of them can be switched off, and the data are still actionable, they are still available. And here we use some colors to also show you that our erasure coding scheme, which we are using, which is for every 6 pieces of data, we are creating 2 pieces of parity. And this is how is it distributed across the servers. You can see the colors. So you can see here like 3 pieces of data, 1 piece of parity. 3 pieces of data, 1 piece of parity. So this yellow color is here to indicate the parity parts. So I will be using this picture for a moment to describe a little bit more of the functionality. Let's move on to the next slide. And so selective write grouping in our typical deployments is also, we are using currently the highest available bayable also that we can buy it basically with big quantities hard drives in the market. And as of the day of this presentation, such hard drives are 28 terabyte host managed SMR drives. However, there are already drives, 32 terabytes host managed SMR drives, which are announced by the Western Digital, which also are already being delivered to the storage providers, including also to us. We are going to, from the beginning of the year 2025, we are going to deploy storage based on the 32 terabytes host managed SMR drives. There are very special one. They are, first of all, supporting the power disable support feature, and also they are coming with the OptiNAND technology, which is delivering some extra interesting features for this 256 megabytes zones management and caching, which is inside of the hard drive. So moving on, what is very important about this particular hard drives is that they are using very little electricity. Contrary to this, what is an opinion about the mechanical hard drives, not everybody knows that the hard drives are using very little electricity. And if you take a look at this 28 or even 32 terabytes factor, when you have very huge capacity and you suddenly correlate it with the number which is 9.4 watts of energy only, maximum energy usage per hard drive, suddenly you can see that even extremely active hard drive based storage is not going to use so much electricity. What is interesting, many people also is falsely thinking that NVMe drives are, because there's only electronics, because there is no mechanical parts, are using less electricity. And this is a common misconception, at least currently as year 2024. The NVMe drives are using much more electricity per terabyte of data than mechanical hard drives. This is also possible because these hard drives inside, they are filled with helium, and the helium is working a little bit like lubricant for the rotary drives, and these rotations are meeting very little resistance after the drive, the disks are being spinned. So this is one of many reasons why this drive is using less electricity. But what is important here is that we can go to all of these levels down with electricity usage, with the power usage, power consumption, down to the zero. So the solutions which are not supporting power disable features, pin number 3, they cannot go below 1.2 watts of energy. But if you have this extra ability to switching off the hard drives, you can actually put it really to the 0 watts of energy. So another very important parameter of this hard drives is how much time it takes to make data available to me. So usually the hard drive, when it's in the idle sleeping mode, let's call it, it's like idle, not really working mode, let's call it, it is taking 1.5 seconds to again start delivering data super fast. And there are other states like 4 seconds. Here you can see 15 seconds. And then is the most interesting for us slides value in this table, which is what happens when the drive is completely off, how much time it will take for my data to be available. And we're talking here about 30 seconds. Yes, half minute. Half minute is, this is the time when your data are ready to be streamed to you with the speed of 10 gigabytes per second from our storage solution. And you can start using them from the state when there was a 0 electricity consumption from the hard drives. So I hope that these numbers are impressive. They're certainly impressive for me. And you can start thinking about this, how to build new storage systems based exactly on this extra feature, switching off the hard drives. So I was talking about this moment ago that there was an implementation called MATE, which is a massive array of idle disks. And we have a different take on this MATE mostly because of the also bad press, which is around the MATE. Even if our solution is similar, we decided not to call it a MATE, but we decided to put a significant difference in the naming. And we decided to propose something which is called Infinite Code Engine, which is basically new approach, working approach for managing huge quantity of the drives, massive arrays of drives in the idle or even off state. So this is just, I wanted you to remember that if you see the eyes in the context of storage, this is what we are thinking about. We are thinking about something which can be frozen, and in infinite quantity of drives can be used and connected to this grouping. And also we have few phases which we are implementing to make the eyes complete. The first phase, which we already did, is supporting for the host managed SMR drives, which are the highest density drives in the market. The second phase is now, and this is implementation of the write grouping concept. And this is what we are presenting on this presentation. And as you can see, this can provide people with 43% better energy saving than if they would decide not to use write grouping concept or not to use host managed SMR drives. And for the next years, we are thinking to do some better data placement, smart data placement implementation, which will a little bit increase this to the 50%. And naturally, everybody is talking nowadays about artificial intelligence, about LLMs, about this, what this technology can do. So in the year 2026, we believe we can have some interesting proposals regarding this, how to apply this technology in the storage to further improve and increase the energy saving up to 70%. So the first phase, I already talked about this, so I don't want to stay too long about this slide. It was about host managed SMR drives. We have done it, and I refer all of you to the presentation which was done last year on the SDC storage developer conference in 2023, when we are talking about this, how our implementation of host managed SMR drives in the open source distributed file system is looking and how we did this. So I encourage you to go there and see more about this. Regarding the second phase is exactly this. What is this presentation about? So selective write grouping. And we will be talking about big clusters, okay? So in order to have an advantage about the cold data, let's call it not only cold, but the one which are in the middle, which is called partially cold data, okay? And the hot data, in order to have advantage of these states, we need to have big storages. So we are talking here about, let's say, minimum 480 hard drives. It doesn't mean up to 816, but this is like minimal installation, which we are talking 400, 800, and 800 drives, okay? It depends also what kind of JBoss you are using. And also our original implementation, which we have before we applied the ICE, was using regular chunks in the balanced way among all of the available drives, which means that the data will be equally distributed across entire cluster. This is how we used to do it before the ICE. So if you see here 800 hard drives, or on this picture is 480 of them, so it's 8 servers, each of them 60 drives, we would be filling the storage in the way that proportionally, first drive here, then first drive here, proportionally, all of these drives will be filled together, yes? So bear with me, because I'm going to show you how we change this approach with the selective write grouping. So first of all, the balance strategy was not working. The equal balancing was not working for us because of the same reasons which write groups are not working in the made systems, which means in order to switch off one drive, actually we have ability to switch off all of them, which is impossible in the storage because the data must be available. In other words, we cannot just stop the drives for very particular file or very particular directory. We just don't have this ability in the old-fashioned way when the data were equally distributed. So what we propose is that we will create something which we called write grouping, which means we will select the row in the servers of the disk, like here is the row number 5 selected, and we will call this row, we will call it write group. And from now, the data is not going to be distributed across entire cluster, all of the servers, all of the hard drives, but only inside of this write group. Here is called WG5. And you can see that on this cluster, we can create few such groups, and it gives us ability to move across these groups from the level of the one which are the most cold to the level which are the most hot ones. On this slide, you have an example when the blue color is showing the cold data on the same servers, when the group number one and group number 2 is cold. The same is about the group number 6 and 7 and the last group. All of them are cold. And it means that actually all of the hard drives in this group are completely switched off. And then we have a yellow group, which is becoming cold. Soon it will become cold. And we have some reasons to believe that it's going to be cold. Then we have another group, which is called warm data. This is the group which just a moment ago was very hot, and now it's just entering to the state of becoming warm only. And of course, we have active group, the one which is actively being used for creating the new data, maybe also reading the data. And this is something which is called hot data group, the group number 5. And what I also wanted to mention is that not only the rows which are cold are switched off, but actually the moment when we stop considering writing the data to the group yellow, for instance, and to the group orange, we don't create the new data there anymore because there are already full of data. When we achieve this, it's a little bit like you have a tape and you completely fill this tape, then you don't need to use it anymore and you can switch it off, you can put it on the shelf because no new data is appearing. So I just wanted to say that in our case, we are switching off in this even cold, nearly cold state, the yellow and orange, we are switching off even all of the parity drives because these drives are completely not needed for anything. Even if somebody still is reading a little bit from the yellow group, even if somebody is reading a little bit from the orange, it's fine. They can still read it from the white drives which are on this picture. However, the parity drives, which are there just for protection, can be completely switched off. And if you think about this, that we actually can switch off all of the parity drives, and the only one which needs to be on are the group number 5, because that's the only group which is creating the data across the servers, then suddenly we are looking at the 25% warranted energy savings. We literally are switching off 25% of the parity drives, and the only one which are on 25% of all drives which are parity drives, and the only drives which are on are the drives in the group number 5, including the parity ones. So this is also worth of noticing here. So now I would like to talk a little bit even more about the details, how we implemented it, so how we did it. Okay, so first of all, we are using a distributed open source file system. It's called SaunaFS. It is being developed by us. It's available on the GitHub, and it's written in C++. And what you need to know is that it has very similar architecture to the Google file system, which was introduced a while ago. And it's allowing you to distribute your data in the 64 megabytes chunks with the 64 kilobytes blocks across your cluster and servers. So first step is in our implementation was to use SaunaFS as a base. Also, what is important maybe that this SaunaFS has also built erasure coding and also has checksums, which allows to be sure the data is extra protected. So we didn't need to build our storage based on the ICE engine. We didn't need to implement this part because we already took ready file system, which we are maintaining and which is available on GitHub. So what we needed to modify in this file system was a very little change, which is to point out that some data is being stored in the metadata part, and some data is being stored in the regular drive. So there is a metadata drive which is stored in the NVMe, and the data is being stored in the hard drives, mechanical hard drives, for instance, host managed SMR drives. And this is why we need to usually point out where will be this metadata stored and where will be this data stored. Yes, so this is the difference in the configuration which we needed to implement. So another detail which we needed to do for the write grouping algorithm is to implement the new way how we are defining this configuration. So this was the old way, yes, this was the old way which allows us to make this separation, and this new way which we are doing right now is to actually point out which drives will be in what write group. So this is like, for instance, one group which is called staging area 1. This is the group which is called staging area 2. So each of these write groups now can be in our configuration files defined specifically, including the placement of the metadata or the data. Also, we particularly are selecting which drive is going to be for data and which drive is going to be for parities. So this is also the change which we did in the SaunaFS. Regarding the testing frameworks, in order to make sure that our system is correctly tested, we needed to extend over 300 tests which we have in our system with the ability to also produce this ICE defined storages. So we can define right now, this is the modification which we added to the testing framework, which is like how many staging areas we are going to have and how many write groups we are going to have in the cluster. Also, there are other parameters which are defining how many basically rows of the drives will be there, or what is the width of these groups, which is just helping basically to define how big are the groups, how many petabytes or terabytes they have inside. And we are still using something which is called null BLK to emulate the devices. And so this was not changed in our storage. What we needed to implement is a new disk manager. And this new disk manager is allowing us now as a plugin, enable the SaunaFS to also have advantage of providing the status of the groups, manage the power states, and disable electricity if it's needed on the hard drives to put them in the lowest possible state of the energy. So we did it by extending the class of disk manager in the SaunaFS. And of course, we need to manage particularly the garbage collection mechanism, because there's a disk manager, for instance, for the host managed SMR drives, which requires this kind of garbage collection. So we need to take into the consideration the very special other states, like, for instance, fragmentation, garbage collection, which is happening in the host managed SMR drive. So we needed to extend this disk manager for ICE with these functionalities. And also, we need to be sure that the rebalancing is working across the group. So as you can see, here is the example when the data are perfectly balanced. And on every drive, you can see it's almost exactly the same quantity of the chunks, which is dictated exactly by the balancing algorithm. So another challenge which we had was that when the people are buying from us almost 3 petabyte storage for their archive based on the hard drive. So they buy 8 servers from us, and then they would like to grow the storage. It would be great to offer them ability to grow, let's call it gradually, so step by step, without the need of buying exactly the same size storage again. The investment for 3 petabyte storage is sorry, actually, I mean, it is not 3 petabytes, it's much more, right? If we multiply 100 drives with 30 terabytes. It's actually even more, right? The point is that such big investment for 10 or 20 petabyte storage, it's big enough that people cannot afford suddenly when they need to grow because they're about to run out of space to buy again exactly the same storage. So we are thinking very hard how to allow in the selective write groupings the people to grow the storage. And we came up with this algorithm which allows us to distribute the data in the way that servers always can be protected, that any random two servers can be switched off, and at the same time you can grow your storage with only one added server with JBoss, not 8 of them at the same time. Of course, doing it with 8 is trivial because then we just add another 8 and we don't need to do any rebalancing. It's just new, fresh space. But in order to answer the need of growing gradually, partially, we introduce this algorithm. So please look at this screen. We have here 8 servers again. This time, every server is one row. And we are showing here write groups, which one column represents the write groups, okay? And the one which are on the left sides are completely full. They are completely full of data. And the one which are on the right side, the red ones, are the one which are being actively used to create the new data. This is the active group. So, and now we need to talk about this, how to add another group number 15 and number 16 to this storage without destroying the properties of the system. And we can achieve it by adding, of course, only one server on the bottom, which is empty on this slide. It doesn't have any data on it. And then what we are doing on the existing completely almost full storage, because as you can see, only the group 15 left to be used, we are selecting diagonal here. This diagonal is not accidental. It is exactly selecting one row of the drives from every group different. And this allows us to put all of this data on the new server. So if I go to the next slide, you can see that the new server can receive all of this data from the diagonal. And this way, the data which was in the diagonal can be now freed and used in the very safe manner to create the new group, the group number 16, which will be here in the moment presented. So first we delete the data which we just had in the original archive because we just moved them to the new server. And then we are able to create the new group, the group number 16 and the group number 24. So we are repeating this step of creating the write groups when we can put it on the server, and then we can select another diagonal over here when we can put another pieces of data in the same server, which will even more to optimal use the newly added space. And right now, this cluster has all of this white space, free space, all of this one free space, all of this which is here free space, and even we have ready the entire group 15, which is available. So which is translating to around only 5% wasted space at the moment when we grow the storage with one server only. And then we go to another step when we add another server. And as you can see on another server, we again draw the diagonal. We remove all of this data. We put it in this new server, and I go another diagonal here. We put this other data which left here. So continuously, we are creating a lot of diagonals, which we managed to clean up on the existing old storage, and we able to grow our storage by adding one by one server without destroying the properties on the storage. Properties which allow us to any random two servers to be switched off. And what is beauty of this algorithm is that after we added the 8 servers, we can actually continue. We can go with another diagonal and another diagonal and another diagonal and adding it to the new server, and so on and so on. So there is an ability, thanks to this algorithm, to make sure that the data are growable the storage is growable in only one server at the time without destroying the properties of protection of the data and even without the need of switching electricity on the hard drives. These drives which were here are completely sleeping. They are never needed to be switched on during the process. The new drives which have been created here are also going to be sleep after they were moved. So only for a moment they were turned on, the data were copied, and they again can go sleep. So all the properties of having the cold data and protection of the data are preserved, and the growing is step by step. So I'm almost finishing, only 10 slides left, so still please bear with me. So what is very important is that all of these changes in our storage by us are still allowing system to perform a regular maintenance tasks, which are garbage collection, which is needed for the host managed SMR drives, and which is data scrubbing. So when you think about this, that every storage system, no matter if it's a big one or small, every storage system needs to be turned on from time to time, and the data needs to be scrubbed. So because this is also true for our storage solution, we are using these moments for scrubbing the data to actually perform rebalancing and redistribution of the cold and hot data to another levels between the groups. So this is like using the advantage of the fact that we are scrubbing the data to providing the access to the data and providing the garbage collection tasks at the same time. Another interesting thing which I wanted to show you today are some results. So this example storage, which was built from the 60 drive JBOD system, we implemented it on our laboratory before just sending it to the customer. And we wanted to show you that this is the result. So on the beginning, when we didn't implement, we have not enabled ICE, we have all the drives working in the red mode, which is a high energy usage stage. Okay, they were not off. And after enabling the ICE algorithm on top of our storage, you can see that there are clearly visible drives which enter to the mode of completely being switched off, also to be in the middle in the orange, and also to be recognized as the one which are in the sleeping state. And the red ones are the ones which are actively being used to create the new data currently in the storage. So the implementation was a full success, and we managed also to implement our diagonal algorithm for the growing. And to conclude, I just wanted to tell you that the infinite code engine is bringing you to another level of the green, efficient storage solutions, which allow your data to be actionable, and it's implementing the power management features together with the workload skew capabilities of our system. And all of this was implemented on the SaunaFS platform. So SaunaFS platform is available for free as an open source product. However, the plugin ICE is currently the proprietary part of the system, which could be added for everybody who is interested to having this kind of the properties in the storage. Or hopefully, all of you who watch this presentation, you can in your storage learn how you can implement your own workload write grouping scenarios. What is next coming on our side? I already said that we are working on the data distribution challenge in the way that we can do it in the scale method. And also, what is important is that this data distribution challenge is impossible with the traditional method. So this is why we needed to use the this new approach, which allow us to do it in the ICE way. And I think I already talked about this, so this slide is accidentally repeated on this presentation. So I would just move on to the very end, and we just tell that the next phases which we are going to do is going to be the smart data placement with the feature of artificial intelligence or maybe other heuristics which we will try to apply in our storage to make it even more effective from the point of view of the energy efficiency. So stay with us, come for another SDC conference. We are going to have a new presentation about another step about this, what we managed to achieve during the next year in the energy efficient storage. So thank you very much. That's it, what I prepared for today. And hopefully I will see you next year on the SDC. And if you would like to contact us, it is possible through our email addresses or through our webpage. We are a company which is producing the storage solution. We are Lail Storage from Estonia, and we are very happy to talk to you about your challenges in the highly efficient energy storages. Thank you very much for your time.